Alright, let's see. We should be back. Someone let me know if this is working alright. Okay, cool. I'm going to give everyone a minute or so to get back, because unfortunately there were some problems. Starting the last stream, I had it pulled up in some other tabs, and so there was a pretty nasty echo. But hopefully everyone should be able to trickle back in at this or now. So, okay. Yeah, why don't we go ahead and get started, and then hopefully we can quickly knock out the first two problems, and then probably the most interesting ones to go over will be I guess most of the ones from Div 2. Kostav asks, will you tell the Div 2 solutions too? Yeah, I'm going to be going over the solutions to all the problems from the contest except I don't know full solutions to Ancient Magic and Matrix permutations, the two hardest Div 1 problems, so I'll be going over solutions to all the Div 2 and Div 3 only problems, and then the other problems in Div 2. And then for the Div 1 only problems, I'll go over solutions to the subtasks, but I won't be able to go over the full thing. And someone says, can you increase the font size? Yeah, before the stream, I increased the font size for my editor to 16 point. And I've done the same with my notepad, so hopefully that works out nicely. Okay, so we're just going to go easiest to hardest, so we'll start with the first few Div 3 problems, and we'll continue from there. So let's start with Sheffden spells. We have 3 spells. Their powers are A, B, and C. Initially you have 0 points, and if you use a spell with power P, then you gain P points. You want to use exactly 2 spells out of these 3, and your goal is to find the maximum number of points you can have after using the spells. So this is a pretty direct implementation problem. You're just going to find the largest 2 values and add them to create the answer. Should be pretty immediate after reading the problem. Because obviously the spells if you're trying to maximize your number of hit points, you're going to use the 2 most powerful spells. So the code is pretty short. The way I do this particularly concisely is I just read in A, B, and C as a vector of length 3. I sort it, and now A of 0 is the smallest value, and then A of 1 and A of 2 are the larger 2, and so I print out A of 1 plus A of 2. Should be pretty straightforward. Okay, so let's see. Actually, before we go any further, I'm going to set up a zoom so that I can use my notepad. Okay. Okay, so iPad can share, and okay. All right, perfect. Okay, so now let's look at the second problem. Sorry about that delay. Okay, red alert. So there's going to be rain in the upcoming N days. Initially, the water level is 0, and on day I, the amount of rain can be described as an integer a sub I. And if it's positive, then the water level increases by a sub I. But if it's 0, then there's no rain, and the water level decreases by d. But the water level can't be negative, so if it's less than d beforehand, then it becomes 0. And so we need to check whether at some point the water level will be strictly greater than h. So this is a fairly straightforward simulation problem. Essentially, we're just going to go day by day, and we're going to compute the water level at each day, and then I'm going to maintain this variable found, and that's going to store whether or not a day with water level greater than h has been found yet. and then in the end, if such a day has been found, then I print yes, and otherwise no. Now you might wonder, how do we maintain this variable? So I'm going to store cur, which stores the current water level, and then I read in x, and if x is positive, then I add x to the current water level, and otherwise I subtract d. Now then I set cur to the maximum of cur in 0. Remember that check max cur 0 is equivalent to cur is equal to max of cur 0. And then if the current water level is greater than h, then I set found to true. So again, a pretty direct simulation and implementation problem. Let's see, questions in the chat. Someone asked, can you solve div2, please? Yeah, I'll be solving the division 2 problems next. Okay, cool. So let's move on to beautiful pairs. So we're given a sequence a sub 1 through a sub n, and an ordered pair of indices I comma j in this sequence is called a beautiful pair if I is not equal to j and this inequality holds. We need to find the number of beautiful pairs present in the given sequence. All right, so this is where I need my notepad, because we are about to do some math. So this expression, I don't know, maybe it doesn't seem immediately that easy to work with. So what we're going to do is we're going to try to manipulate it to make it less messy. And immediately, one thing we might think to do is clear the denominator so that we're not working with fractions. And so that gives us that this inequality is equivalent to a sub j times, that's a terrible parentheses, a sub I plus, or sorry, a sub I minus a sub j is less than a sub I, a sub I minus a sub j. Okay. And so that gives us ai aj minus aj squared is less than ai squared minus ai aj. And if we move this all over to the same side, then we get a sub I squared minus 2a sub I a sub j plus a sub j squared is greater than 0. Now, some of you might remember that this left-hand side actually factors really nicely. This whole thing is equivalent to a sub I minus a sub j squared is greater than 0. And recall that the inequality x squared is greater than 0 holds whenever x is not equal to 0. And so what that means is that this inequality holds whenever a sub I minus a sub j is not equal to 0, or equivalently, a sub I is not equal to a sub j. All right. So what we've derived here is that we're saying, okay, we can rephrase the condition as an ordered pair ij is good if a sub I is not equal to a sub j. And so now we need to count the pairs where a sub I is not equal to a sub j. And the way we're going to do this is called complementary counting, which, if you're not familiar with that, it's a really good technique to know. The idea is that if you want to count, or is that you count the number of pairs that are not good, and we subtract them from the total number of pairs overall. So the total number of pairs overall is just going to be, if we're requiring that the indices have to be distinct, there's n choices for I, and then n minus 1 choices for j. And then now, so then we need to count the number of bad pairs. So ij such that a sub I is equal to a sub j. And the way to do this is, suppose a sub I occurs x times in the array, then there are x times x minus 1 pairs where a sub I equals a sub j equals a sub I. I guess actually let's say that some value v occurs x times in the array, and then this is how many pairs there are where a sub I equals a sub j equals v. We can then count the bad pairs by summing up these values over all possible v. Okay, so let me show you all how this is implemented. So what I do is I just read an n, and then I just store the count of the numbers, or the number of times each value occurs. And so then initially the answer is n times n minus 1, because that's how many total pairs there are, and then I subtract out the bad pairs by iterating over each value v. And in some sense, this map CNT is storing pairs of the form v comma x, and so I'm iterating over each of these pairs and subtracting out x times x minus 1. And that's how this one's done. Prasan says, congratulations on winning $100. Thank you very much. Tonoi Sarwar asks, prefer using fast input method. What does that mean in the problem statement? So essentially, in this problem, there can be 10 test cases, each with up to 200,000 numbers. And so that means there can be 2 million numbers. And in that case, if you use a slow input method, then you might get TLE. And so in C++, you need to use this sync with standard IO 0 command here, or some variation on it, although C++ is usually less bad about input than other languages are. But it's particularly important in Java, because in Java, you're going to definitely TLE in this problem if you're using scanner, and so you have to use buffered reader instead. And I don't know what the details are for Python input, but you would need to be careful about reading input in Python as well. Hello World asks, what's the time complexity of my solution to beautiful pairs? So the complexity is n log n per test case. And the reason is that we are basically just iterating or adding n elements to a map. And adding to a map is O of a log n, or editing a map in general is log n. And so the complexity overall is n log n. And then someone's asking, what's v? So v is just any value that occurs in the array. And here here we're essentially trying to count the number of we're trying to count the number of pairs where a sub I is equal to a sub j, where they both take some common value. V is just the common value that they take. Okay, great. So that's this problem. And so now we're going on to array rotation returns, which is the second problem in div 2, fourth in div 3. All right. So you're given a sequence a sub 1 through a sub n, and a sequence b sub 1 through b sub n. And for each valid I, the a sub I and b sub I are between 1 and 2n. You can rotate b as many times as you want, and then we define a sequence c sub I such that c sub I is a sub I plus b sub I % or mod n for each I. We have to find the lexicographically smallest possible sequence c. Oh, and it looks like there are a few questions before we start with this. So it says we can just take unordered map to get an O of n solution. Yeah, that's definitely something you can do. The reason I didn't do that is that the unordered map can have a very high constant factor, and if you aren't particularly careful, then it can be hacked. Like here, let me. Neil has a good article about this on CF. Yeah, I'll put a link to this in the chat. But it turns out that unordered map is actually hackable, which probably wouldn't be an issue on CodeChef because there are no hacks. But in general, the constant factor can be really high, and so in my experience, it's pretty rare that an unordered map is actually faster than map. And so you're absolutely right that it does give you a better asymptotic complexity of O of n rather than O of n log n. But in general, when I'm in a contest, I use a map or a set rather than an unordered map or unordered set. With that said, obviously, if you're in some sort of job interview and the interviewer asks you to get your algorithm down to O of n, then using an unordered set or unordered map is a great way to do that, because in a job interview, they likely won't be aware of and certainly won't care about things like the potential to hack an unordered map or whatever. But for programming contest purposes, I generally stay away from unordered set and unordered map. So as for all problems which want a pair of indices, is working with the relation given in the statement and making an easy relation between the values of the general idea. I hesitate to say anything about all problems of this variety, but certainly if you're given a sort of an equation in the statement and you don't really know how to work with it, then getting out a sheet of paper and trying to manipulate it until you reach something that maybe is a little easier to deal with, that's always a good strategy, not just for problems about pairs of indices, but in general whenever you have a condition that seems, fairly arbitrary and it's not really clear how it's helpful to you. All right, so back to array rotations. Now, something that you should be thinking is, here I actually am not going to hesitate to generalize. Every problem about finding a lexicographically minimal sequence is inherently greedy. So Hello World says, why we can just store frequency in an array since the max element is 1,000,000. Is this better than map? Yeah, that would achieve a better, well, I know. Well, actually, no. In this case, n plus the maximum of a sub I would be a worse complexity in some sense, like given the constraints in the problem. Actually, wait, no, that would be better. I mean, it's all the same. Like both solutions will pass, but what you're suggesting would also work. And Yajir says the same thing. Yeah, so that would be O of n plus max a sub I, which is roughly as fast on the given test input. Okay, so let me go through array rotations, and then I'll answer questions in the chat once I finish with this, because I'm guessing that there are people who want to hear about this problem. All right, so what I'm going to tell you is that every problem about finding a lexicographically minimal sequence is inherently greedy. And the reason is that that basically what the lexicographically minimal sequence is we minimize the first element no matter how large the rest of the sequence is. Afterwards, we minimize the second element, and so on. And so what that basically means is we can be greedy and we can just try to minimize the first element. Okay. So what that means is that we're going to try to rotate b sub I to position 0 such that a sub 0 plus b sub I mod n is minimized. Because whichever element of b we rotate to position 0 is going to be b sub 0 in the end. And so this thing is going to be c sub 0. So we're essentially trying to rotate such that we're minimizing a sub 0 plus b sub I mod n. And Rajneesh in the chat is kind of giving away the punchline here. He says, why can't we say there can be only two arrays, which can potentially be the answer since all the elements are unique? And yeah, that's exactly the next idea. So we know that we're going to be choosing a b sub I that satisfies this condition that satisfies this condition as our first element of b when we finish rotating. And so let's say x is equal to the minimum possible value of c sub 0. So x is the minimum of a sub 0 plus b sub I mod n. Now, what I'm going to claim to you is there are at most two values of I such that a sub 0 plus b sub I mod n is equal to x. And what this tells us is that there are only two rotations we need to consider. And it might seem like I'm kind of pulling this out of thin air, and in some sense I am, but what the motivation for this is that this a sub I less than or equal to b sub I less than or equal to 2 times n is a really weird constraint. Because it seems like if we're only concerned about mod n, then it seems like it would work just as well in most cases for them to be less than n. So the constraint that they're up to 2n should be sending off some red flags. Like, you should be thinking, okay, this is not what I would expect, therefore, like, it seems like if the problem author was just making the most obvious choices at any given time, they wouldn't be setting the limit to 2n. And so that tells us, okay, since this is a little weird, it's probably important to the solution. And so then you realize, okay, these are pairwise, and so then you can get to this claim by using this constraint along with the pairwise distinct elements constraint. So let me explain what I mean by that. So suppose a sub 0 plus b sub I equals x mod n. Then that implies b sub I is equal to x minus a sub 0 mod n. But realize that when b sub I there are only 2n possible values, that means that there can only be 2 values of b sub I congruent to x minus a sub 0 mod n, because there are only 2n values in total. And so that means there are only 2 values of b sub I that can be rotated to become b sub 0. So what do we do now? The first step, we find x. It's just the minimum of this value over all I. The second step is we find values of b sub I such that b sub I is equal to x minus a sub 0 mod n. And then the third step is we're going to pick or generate the we're going to generate the possible sequences C based on these b sub I. And the fourth step, we're just going to output the best one. And because there's only 2 sequences at most, we can compare them really efficiently. So let me show you my code. Okay, so what I do here is I read in A and B, and then I store this array, and then I'm going to do these first 2 steps kind of in parallel. So what I do is I'm letting best be the value of x, and I'm letting vals be the positions in B that generate x. And so what I'm doing is I'm saying, first of all, so what this does is this says, okay, set best to the minimum of best, and then that math thing, and execute the code inside this expression only if ... is actually less than best. So, and if that happens, then what I'm saying is, okay, all the valid positions in B that generated whatever the old best value was are now irrelevant. But now, if this value of B generates the best value of X, then we have to push I to the set of potential values. And so now we have this set of potential positions I. And so what I'm going to do is I'm going to create a vector of vectors called ops, short for options. And then I'm going to iterate over every possible rotation. And I'm going to figure out the current option. And what I'm going to do is I'm going to generate position I of C by taking A sub I plus B sub I plus A mod n. That's how we rotate by A. And take the whole thing mod n to get, because that's the formula for C. And then I push back C. And now there's a convenient trick for comparing the vectors. What we can do is we can just use the sort function on the vector of vectors, and that'll get us the lexicographically, and then the vector that comes first will be the minimum vector. And so I iterate over the elements of the minimum possible vector and print them out. I've gotten a few questions in here about like what do we do if the elements aren't pairwise distinct? What happens if there's no constraint on up to 2n? The answer is this solution is no longer going to work. I don't know if there's a clean way to solve, or I don't know if there's like a clean way to solve it for larger values. There certainly isn't like an obvious one, but I don't know if you can do anything particularly fancy here. but you do need, but both those constraints, the distinct elements constraint and the less than 2n constraint, are necessary for this solution to work. And then I'm also asked, what does it mean that the sum of n over all test cases does not exceed 2 times 10 to the 5th? So this means we're dealing with up to 100 test cases in each file. That's what this constraint t means. This is basically saying that when we sum up n over all test cases, in total it's going to be at most 2 times 10 to the 5th in each test file. And so what that means is, and the reason that's important is, we've got a time limit of 1 second for this problem. And if we weren't given this constraint, then the problem could feed us 100 test cases, each with 10 to the 5th, or each with n equals 10 to the 5. And so we could have to read 100,000 elements into our arrays 100 times, and that could be really slow. So this is telling us, this constraint is saying, okay, the sum is only going to be 2 times 10 to the 5th. And so like if n is actually 10 to the 5th, then there would only be 2 test cases of that size in a file that you would need to process in 1 second. And so we don't need to worry about having to process 100 of these large test cases all at once. Okay, yeah. So I think there are a couple of themes that you should take away from this problem if you didn't solve it, to hopefully get problems like it the next time. The first is that you should you should always be thinking a greedy strategy whenever you're looking at lexicographically minimal sequences. And the second is that whenever the constraints look a little funny, look like something you might not expect, pay attention to them. They might be important. There's a problem like this on Codeforces a little while back. Let me find it. I think this was from the Harbor Space Contest, problem D, I want to say. Or no, problem E. Yeah, there was this problem here, and I'm not going to go over this whole problem, but there was this 0 less than m less than n over 3 constraint, and that immediately you should be thinking, okay, this bound has to be important, and indeed, this did end up being the solution to the problem. So in general, look for weird constraints in problem statements and try to abuse them where you can. Weird constraints being anything that you wouldn't expect, or also you want to pay close attention to any constraint that's really small, so something where a number is bounded by like 15 or 20 or something like that, because for those you might be able to do an exponential solution. Hello World asks, will that sort work for string as well? Yep, totally will. Same exact method works for strings. Okay, so that's all for array rotation returns. Nast says, why don't you use Linux as your main OS? I'm pretty reliant on a number of applications that work only on Windows, and so I wouldn't really be able to use Linux full-time without dual booting all the time, and that would just be too much of a pain for me to deal with. The other issue is that Linux doesn't really play nicely with most peripherals because, like for example, mice and keyboards and stuff are typically built with Windows and Mac compatibility in mind. And so I found that when I tried to use Linux, something which I did for a couple of months last year, something would like break just about every week, and I'd need to take several hours to figure out what's going on and try and fix it, and it just got to be really frustrating really quickly. Eventually, like what really made me throw in the towel was when Linux stopped taking in audio from my mic, and I couldn't figure out why, and then I was attending classes online, and so I needed my mic to work, and so that was when I decided, okay, screw this, I'm switching back to Windows. QXP asks if there was no constraint saying that the values were only up to 2n, then is this question doable? Not using the solution I came up with. I discussed this in a bit of detail a few minutes back, so if you're curious, you can rewind a little, and I talked about it there. All right. So now we're moving on to the div1 problems. As you all might have noticed, let me see what the final scoreboard looks like. But it was pretty clear that there was a very significant difficulty jump between array rotations and then longest good segment, which is the next problem. All right. So longest good segment. We have a sequence a sub 1 through a sub n, and we're calling a contiguous subsequence of a segment. A segment is good if it can be divided into at most k segments, such that the sum of the elements in each of those subsegments is at most s. You need to find the maximum number of elements in a good segment. Okay. So let's start with a little sub problem, and this is where it can be really helpful to look at special cases if you're not sure how to if initially the problem seems a little bit tricky. So let's think about what happens if k equals 1, or alternatively, suppose we want to build a good segment starting at position I. How many elements can we include? And can we answer this for all I? So what I'm going to show you is that we can compute the length of the longest valid subsegment starting at each position in O of n using 2 pointers. And let me show you that in my code because I think that's going to be the easiest way to explain this. So for now you can ignore this, or you can ignore the fact that this has the second dimension of length 19, but what I do is I read n, k, and s, and then the sequence a, and then I maintain this pointer p equal that I initialize as 0 and the current sum. And then what I say is while our pointer is at less than n and we can add a of p and our subsegment will still be okay, let's add a of p and increase p. And then I'm letting next of I of 0. Next of I of 0 is the position immediately after the longest valid segment starting at I. And so next of I of 0 is equal to p because p is the first element we couldn't add. And then afterwards I shift the left pointer, I remove position I from the sequence by decreasing the sum by a sub I. Okay, so that's how I build this next of I of 0 array. Now the motivation for doing this is this problem, it's a lot easier if you're familiar with a technique known as binary lifting. So, and binary lifting is essentially saying, given this sequence next of I of 0, we can compute the let's see, what's the right way to say this? The length of the longest good segment starting at position I in O of n log n for all I. And more generally, what we can do with binary lifting is we're going to say, okay, so we know the length, let's see, so what's the best way to explain binary lifting? I'm actually going to see if there's a article on CP algorithms I can go, I can go over because I think that would be helpful. But yeah, I think this LCA one would work. So basically, binary lifting is something you might be familiar with from computing lowest common ancestors in a tree. If not, then don't worry, we'll be going over the more general explanation. But basically, in the context of a tree, what you do is you build an array up, where up of ij is the 2 to the jth ancestor above the node I. And so then what we can do is suppose we want to get the 5th ancestor above I. Well, then we can write 5 in binary. It's 1, 0, 1. And so we have this. And so we can write it as 4 plus 1 is its binary representation. And so then using up of I of 2 gives us the 4th ancestor above I, and then up of I of and then up of this value of 0 gives us the first ancestor above this value, or the 5th above I. And so we're doing a pretty similar approach here. What we're going to say is next of I of j stores the first position after a segment from which we can construct 2 to the j good segments starting from I. And so next of I of 0 stores the longest valid segment containing just one subsegment starting at I. And then what I can say is, so let's say j equals 1. So next of I of 1 is going to be the position after 2 valid segments starting at I, and that's equivalent to the position that's 1 good segment after the position 1 good segment after I. And so that's the idea here. If you aren't familiar with binary lifting, I would encourage you to read about it. I can put a link to this article in the chat. But that's that's a pretty critical idea to solving this problem, I think. If anyone knows of a way to do this that doesn't involve binary lifting, please feel free to let me know in the chat. I'd be happy to go over an alternate approach if it would be helpful. But okay, so then you can build this next of ij array, and again, details on that are in this article, like you can see there in this code right here. And then we can use binary lifting to find the kth segment after any given we can find the point after k segments after any given point by essentially iterating over k's bitwise representation. And so what I'm going to do is I'm going to iterate over the powers of 2 in descending order, and while we have at least 2 to the j segments left, I'm going to set p to the next of p of j, which essentially takes 2 to the j segments. And then p is the first element that isn't included, and I is the first element that is included. So the total length of the interval is p minus I, and so I set answer to the maximum answer in p minus I. So yeah, that's a problem. Again, might not make much sense if you haven't seen binary lifting before. If you haven't, I would encourage you to read some articles and then upsolve. I'm going to look. I want to see if there's a more general article, because there are a lot of there are actually a lot of applications of binary lifting that are not LCA. Yeah, let's see. So here's a couple of practice problems, and here's someone's video tutorial. Obviously, I haven't vetted these resources myself, but if you're looking to learn more about binary lifting, maybe you'll find those helpful. All right, let's look at questions in the chat. QEXP asks, is it possible to optimize the solution using binary search on the number of elements, and to get it from from n squared time complexity to n log n? That's a good question, but I don't think it is. And the reason is that we're going to need O of n well, yeah, I think there are 2 ways I can sort of visualize this. I could think about it as we're just going to binary search on the number of elements, and we just need to check if any array of this number of elements is good by this definition. But in that case, I'm not sure how you'd write a checker in a complexity better than O of n squared. And the other way I could see it is iterate over each possible first position and binary search over the second position. But then that would be O of n binary searches, so we would need to write the checker really quickly, and I don't see how you would write that checker in less than O of n. So maybe there is a way to do this, but I'm not coming up with it off the top of my head. And someone says, I iterated the array not in the same way by finding the 2 in, I think this is back for array rotations, but someone was saying I found the 2 indices with minimum C and put the answers in 2 different strings and printed the smallest one, but got WA. If you use string, that would be an issue because n could be larger than the number of potential characters. Otherwise, there's likely just a some sort of issue in your code. And then, let's see, going back up a bit, VXD says, do you create a folder for every contest? Yeah, if you look at my competitive programming setup video, I go over my structure, or the structure of my files. I'll put a link to that in the chat if you're curious. But basically, I have this folder vimcp, and that and I have one folder within vimcp for every contest I do. And that helps me keep everything nice and organized while also allowing me to keep really short, concise file names for my code. Okay, cool. Let's look at XOR separation. Someone says, I wrote binary lifting for checking and then binary searching on the answer. Can you go over how you avoided this? Yeah, so I think once you write the binary lifting, you can finish the problem fairly directly from there. And the idea is that we can and the idea is that if we're trying to get the position after k segments, what we do is we iterate over the powers of 2 in decreasing order, and then for each power of 2, while we can take that power of 2, or like for each power of 2 to the j, while we can take 2 to the j segments, we subtract that number of segments, and then we take 2 to the j segment site by setting p to next of p of j. And so I'm not sure what a binary search approach would look like, but this shaves off a log factor from that, so n log n. All right, next problem. XOR separation. So you're given a sequence a sub 1, a sub 2, a sub n, or up to a sub n. And you have to find the number of ways to split it into at least one non-empty contiguous subsequence b sub 1, b sub 2, up through b sub k, such that the following condition is satisfied. For each I, the XOR of all elements in b sub I is divisible by 2 to the I minus 1. All right. So here's what I'm going, okay. So this one, let's do some observations. So realize that the XORs of the subsequences b sub 2, b sub 3, all the way up to b sub k are all divisible by 2, i.e. they all have a 0 in the first bit. So moreover, the XOR of the whole sequence A is equal to B1 XOR B2 XOR B3 up to BK. And so what this tells us is if all of these XORs with, if all of these have zeros in the first bit, then, in the least significant bit, the XOR of A is equal to the XOR of B sub 1. And so what that means is we need to pick sequence B1 such that the XOR of the elements in B1 matches the XOR of A in the first, sorry, I'm blanking, in the least significant bit. Now, what about the next power of 2? What about the next bit? So the XORs of B3 up to BK are all divisible by 4. So and so that means that B1, or that if we're looking only at the bit corresponding to 2, only B1 and B2 can have this bit set because B3, B4, etc. are all divisible by 4, so they're not going to have. So they're going to end in 2 zeros. So so only B1 and B2 can have the second to last bit set. Okay, so what that means is that all of these things are going to be zeros in the second bit. So in the second bit, i.e. the bit corresponding to 2, XOR of A is equal to the XOR of B1, XOR B2. And we can generalize this. So what we can say is the XOR of A is equal to the XOR of B1, XOR B2, XOR B3 in the third bit, and so on and so, and B1, XOR B2, XOR B3, XOR B4 in the fourth bit, and so on. Okay. So what this tells us is is whenever we end sequence I, b sub I, b sub 1 XOR b sub 2 XOR up to b sub I must match A in the smallest I bits. Okay. And so what I'm going to do is I'm going to do some DP, where DP of I of j represents the number of ways to I guess let's see, to be consistent with my solution, I'm going to say to place I elements in the first j plus 1 sequences. The first I elements in the first j plus 1 sequences. And to transition, first of all, we can just not start a new sequence. We can add a new element to the same sequence. And then, if the XOR of the first I elements matches XOR of A in the first j plus 1 positions, then we can add dp of I of j. I guess actually here, sorry, j plus 1. If it matches in the first j plus 1 positions, then we can start a new sequence because we have the match that we're looking for. Now, there's one catch. So notice that there's no bound on k. K can be up to, like, we could theoretically just start a new sequence every time. Like, if A were all zeros, then we could just have every element of A in its own sequence. And so then j could go up to 10 to the 5th. But here's the observation. After the most significant bit of XOR of A, XOR of A is always 0. So the condition under which we can do our dp of I plus 1, j plus 1 is equal to dp of I of j transition is always just that the XOR of the first I elements matches XOR of A entirely. Once the j plus 1 bit or 2 to the j is greater than A. That means that the only number of distinct states we have, that means we only need to deal with log n distinct states, and we'll just take special care of the states that are, or of the states where 2 to the j is greater than A in order to handle them all together. So let me walk you through how I do that in my code. And in my code, I sort of compressed this a little. I cut out the I dimension, so my dp essentially just corresponds to, so this, I have this 57, essentially just corresponding to j. And then I'm just going to update it for each I as we go along. So first I store S, and S is just going to be the XOR of A. And then initially dp of 0 is 1, so there's just one sequence containing no elements with where we're about to start b sub 1. And if you haven't seen MI before, this basically stands for modular int. It's just a data type I use for problems where I have to output the answer modulo some value. Okay. And so then for each of the first n-1 elements, because there's no way to end a sequence and start a new one with the last element, because like if you start a new sequence after element n, there's no elements to put in the new sequence afterwards. So what I do is I maintain x, which is going to be the XOR of the first I elements, and then I XOR it with a sub I, and for all j, so the fact that I'm keeping this 1DP array automatically takes care of these transitions, so I just need to process these transitions. And what I say is, okay, so x and 2 to the j minus 1 is going to get me the first j plus 1 bits, or the smallest j plus 1 bits of x, and the same thing for s. So I say, if the first j plus 1 bits of x are the same as the first j plus 1 bits of s, then I can add dp of j minus 1 to dp of j. And then the one catch is in this maximal state. So I calculated that 2 to the power of 56 is going to be greater than 10 to the is going to be greater. It's going to be significantly greater than a sub I, and so it's going to be greater than the XOR of a. And so if this is the case, then we can also transition to this last state from itself, and that's to handle the case where all the cases are distinguishable. Like this is essentially saying that we can transition from 56 to itself instead of going from 56 to 57. Okay. Yeah, so that's the problem. Any questions about this one? For subtasks, by the way, so I think this one and up to 20, I'm guessing that you were supposed to just do a 2 to the n solution and iterate over just iterate over which elements you start a new sequence with. With n up to 2500, I think the idea is to allow for slower implementations of this dp and o of n squared, where you iterate over each sequence. And then I'm not really sure about n up to 200, how that makes the problem easier. Yeah, I don't know. If anyone has any ideas for how n up to 200 makes the problem easier, please feel free to share them. I can definitely see how 2500 makes it marginally easier, but 200 I don't really get. Wonder how many people solved it. Yeah, I mean, I guess there were 12 people who got 200 but not 2500. I wonder if it's just less efficient implementations of that solution. Okay. Anyway, let's look at problem C, bad luck. And this is, so I think XOR separation, I believe, was the last problem in Div 3, and this is the last problem in Div 2. And then afterwards, we'll get to the Div 1 only problems, but again, I don't have full solutions for those, so I'll just be going over subtasks. All right, so we have we're going to, I don't know why they gave us this flavor text about a magic circle when there's literally nothing else about a circle in the entire problem statement. But we're given, we have these n chopsticks, each with a given length. And then for each valid I, the ith chopstick casts a shadow over the range yi to yi plus xi. And the positions of the chopsticks should satisfy an additional condition. For each pair of neighboring chopsticks, I and j, the distances between them must fall in the range L to U. The magic power of the circle depends on the total shadow length, or the union of all of these segments. So we need to find the minimum and maximum value of these segments. Okay, so let's start with an observation. In general, Maxim says, "Hey Maxim, congrats on solving the congrats on solving matrix permutations." Yeah, Maxim says something like iterating over the subsegment ending at index I as well as total number of segments. Oh yeah, that would make sense. Like if you don't have the observation that you can actually reduce it to only 50 states, that would be, yeah. Okay, I bet you're right. I bet that's what it was. Okay. So, all right. So in general, in order to minimize S, we are going, so what we're going to do is we're going to place the chopsticks close together to maximize the overlap of the shadows. And likewise, to maximize S, we'll place the chopsticks far apart to minimize the overlap of the shadows. And so equivalently, what this means is we're going to minimize to minimize S, we'll separate all chopsticks by L. To maximize S, we'll separate all chopsticks by U. Okay. So now we essentially have two different problems where we're going to separate the first we're going to try and separate the chopsticks by L and find the minimum possible value, and then we're going to separate them by U and find the maximum possible value. Okay. Now, for the minimum possible value, let's see. I'm trying to remember. I don't think I proved my solution to the minimum case in contest, but essentially what I did is I just sort the chopsticks in descending order of length, and then place the longest chopsticks first. And I don't have a proof of this, but the idea, the intuition behind it is that if we place the long chopstick first, that'll maximize the number of future chopsticks that it overlaps with later on. And likewise, if we place, and so that way we'll maximize the extent to which this chopstick sort of overshadows other chopsticks in the future. So that's how I handle the low case, and I'll go through my code for that right now. So what I do is I sort, and that sorts them in descending order or in ascending order, and so I reverse to get descending order, and then I maintain my low answer, and then cur stores the current length of the stores the current maximum, or the current length we have left that's going to be overshadowed past the current position. And then afterwards, I either subtract out L before we move on to the next position, or if we have less than L length left, then I just subtract out all of cur, and I add that length of shadow to the answer, and I subtract it from the current amount of shadow we have left. All right. Now, how do we maximize S? So let's think about it like this. I think doing this visually is going to be helpful. Okay, so let's say we have this segment, and let's say 0's here, U is here, 2U is here, and 3U is here. What I'm going to do is I'm going to essentially separate a segment out into the number of total multiples of U it covers, and then the leftovers. So for example, let's say we have this segment that goes to, I don't know, let's say that this length is 3. And so this whole thing is 2U plus 3. I'm essentially going to separate it out into two blocks of length U, and then the 3. And what I'm going to claim is, or actually, hold on, sorry, I need to do a separate claim first. Sorry, the separate claim here is that is that to maximize S, the longest chopstick should always be placed last. And the idea is that that's going to prevent it from overlapping with any chopsticks that come after it. Again, that's an intuitive idea, but not a proof. I'm guessing the editorial will have proofs of everything. But I think the role of these video solutions is more to give intuition than to get bogged down in anything too formal. So then we have n-1 chopsticks, and we need to and then there's going to be a length U between each chopstick, so n-1 times U length to cover, and so we want to cover as much of it, this length, as possible. Okay, and so, like I said before, we're going to separate out each chopstick into blocks of length U and a remainder. If there are at least n-1 blocks of length U, then we can cover the whole n-1 times U range. And the idea is that we're just going, so like, for example, with this 2U plus 3, what we're going to do is we're just going to sort of throw out we're going to place this in position 0. We're going to throw out whatever chopstick in position U. And then at position 2U, we're going to throw in a chopstick that's going to cover the block to position 3. And so on. And if there are at least n-1 blocks, then that's going to be possible. And if not, what I claim is that we use all the blocks. So let's say if they're B blocks, they cover BU length. And then we fill the remaining n-1 minus B blocks with the longest remainders. And so what that would look like is, if we decided that this 3 was one of our longest remainders, then I would just like throw out random blocks that we don't really care about at U and 2U, and then I would put the next important block at position 3U. Okay. So again, not a formal proof. This is saying I tried a couple of ideas. Like, this isn't something that necessarily jumped out at me immediately. And in fact, I initially had a wrong idea that I stress tested before coming up with this correct solution. But but this ended up working out pretty nicely once I implemented it. Like, I recorded my participation in the contest, and I'll upload it later today. But I think what I said was like, okay, I don't know if this is right, but it's going to be faster to implement and stress test it than it would be to prove it formally. So, all right. So what I do is I store vals is going to store the remainder, and tot is going to store the number of blocks. And so I iterate over those. I've still got it sorted in descending order. So I initialize the answer to just cover the length of this longest block that we put last. And so then I sort the values in descending order. And then I add at most n-1 blocks to the answer. And while there are less than n-1 blocks that we've taken, I add a new remainder to the answer. And that's the problem. Yeah, fun problem, a little bit tricky, but nothing we can't handle. Okay. So, let's see, is there anything else I wanted to go over here? Don't think so. I feel like I'm forgetting something, but that's fine. All right. So the next problem is matrix permutations, which was listed. It was listed fourth on the Div1 list, but it actually had the fewest AC submissions. Maxim was the only one who solved this correctly. But it did have a lot of people who got 30 points of partial credit, and I was one of them, so I'll go over the solution to that. All right, so we have an n by m grid, and there are k cannons numbered 1 through k placed in k cells of this grid. Each cannon can fire a ball to any cell whose Manhattan distance from the cannon does not exceed the strength of the cannon. And remember that the Manhattan distance, it's essentially the distance that you get from BFS. You can think about it like that. It's the distance where we get one, or where it's like here. The Manhattan distance from AB to CD is equal to the absolute value of A minus C plus the absolute value of B minus D. And that's and it's essentially equivalent to saying, okay, it's going to cost us one distance to increase x by 1, to decrease x by 1, to increase y by 1, or to decrease y by 1. Okay, so each section, so initially the strength of the cannons are 0, and they increase by 1 every second. And at each second, some cannon fires a ball to a cell that doesn't contain any balls yet. And then the number I gets printed on that cell. And so that gives us essentially a permutation of all of the cells, and we want to figure out what fraction of the permutations are possible. Now, in the general case, n and m are each up to 50,000, but there's no bound on n times m, and so there can be a ton of cells. But in the subtask that I managed to solve, n times m was bounded at 10 to the 6th. And what that means is that for the subtask, we can look for an O of nm solution. All right. Now, the second thing, what you should realize here is that, so let's say that the dist of x of y is equal to the minimum distance from xy to any cannon. Then at time t, the next the next cell to be chosen must satisfy dist of xy is less than or equal to t, because there has to be a cannon within distance t. So what I'm going to do is I'm going to compute dist of x of y using a multi-source BFS. And then I'm going to count the number of cells to satisfy dist of xy is less than or equal to t. And the one thing that we have to worry about is that we don't want to select the same cell twice. But what we can do is we can say, okay, if we choose a cell at time t, then it won't be available at times t plus 1, t plus 2, up to n times m. And so we can essentially just subtract, and so we can essentially subtract t minus 1 cells that have already been chosen before time t. Or I guess if they're 0 indexed, then we subtract t. Alright, so let me show you my code. Wait, oh, sorry, I just have it in D-slow because I was doing a slow solution. Alright, so what I do is I have read NMK and I compute the distance, and this is a fairly standard multi-source directional BFS. So it might be something you're familiar with, but then I store these CNTs, and these CNT stores the count of distances that are equal to I for all I. And so then what I do is I turn CNT into kind of a prefix sum array, except I also subtract the one that was taken in the last step. And so then at this line, CNT of I stores the number of potential of cells that would be valid to take. And so I multiply the answer by CNT of I, and then I divide it by multiplying by the inverse of NM minus I, which represents the number of cells we have left to take. And the idea is that we have CNT of I cells that are valid, and n times n minus I cells in total. So we're essentially multiplying the probability by CNT of I over nm minus I. And that gets us our answer. So yeah, that's how we get 30 points on this problem. I do not know how to get 70 points, so I'm going to be reading the editorial later. I'm guessing you're still going to build this CNT array, but you're going to need a much more efficient way to do it, which I'm guessing involves some sort of fancy math. Okay, last problem, Ancient Magic. So there's a game played on a one-dimensional axis. We're going to have n stones, each described by 3 numbers x, t, and I, or x, t, and c, meaning that the stone will appear at point x at time t and has a value c. If a player is at a point x at time t, then at time t plus 1, they can be either at x or at x plus 1. So they can either stay where they are or they can move by 1. And so the player is able to pick up a stone if they're at the given point and the given time. Each stone can be picked up at most once, and the score of the player is the sum of the values of all their stones. We need to find the maximum possible total score for each number of players p from 1 to I inclusive. Okay, now there are 3 subtasks here before the original constraints, and I actually ended up writing different solutions for each of them. But let's go through a quick observation first. First of all, let's think about, consider the sequence of stones that an individual player picks up. So what we need, let these stones be stones 1, 2, 3, up to k, up to, well, we already used k, so up to m, let's say, just without loss of generality. Then we can quickly see that x sub I has to be less than or equal to x sub I plus 1 because the players can't move backwards. But moreover, what we realize is that a player has to be able, in order to get from stone I plus 1 from stone I, x sub I plus 1 has to be less than or equal to x sub I plus the maximum amount of time distance that can be traveled, which is t sub I plus 1 minus t sub I. And if we rearrange this inequality, what we get is t sub I minus xi is less than or equal to t sub I plus 1 minus x sub I plus 1. And so what that means is that t sub I minus xi forms an increasing sequence, as does x sub I, if stones 1 through m can all be claimed by a single player. And we can prove that these conditions are sufficient for a sequence of stones to be claimed. And so what that tells us is that we can transform t into t minus x, and we essentially need to, both of these values need to be increasing. Vaughn says, hi from the problem set of matrix permutations. Hi, glad to have you here. Nice problem. Okay, so let's see. So that's the first observation. That's really the main observation that you need to make. But let's look at these subtasks and let's talk through one by one how we deal with each of them. So subtask 1 is and up to 15. And as I said earlier in the stream, if we have a bound that's up to like 15 or 20 or something, more often than not you're looking for an exponential solution. And so there are a couple of things you could do here, but what I did is I iterate over the number of over which stones will be picked up and the number of players. And so then I find the minimum number of players for each set of stones, and that is going to be enough to compute the answer because then we can just find the maximum value from each set that can be picked up by most k players. So I show you my code. Let me see where it is. So I read in the data and I create this array events that stores the position, time minus position, and value. And then I have a couple of different solutions written. So here's solution 1. I store the result for each value of k. And then what I do is I iterate over each value over each possible value of k. And what I do is I iterate over the stones in increasing order of x. And then I maintain a multiset storing the last t minus x chosen by each player. And then in order to pick up a stone with t minus x equals k, we use the player with the greatest current t minus x less than or equal to k. And so I'd encourage you to think for a bit about how you can prove this. But yeah, so initially I put k zeros in curve because initially x equals or t minus x is just 0 because x and t are both 0. And then for each stone, if it's a stone we're going to pick, then I get this upper bound gets the first player with a larger t minus x. Then I subtract 1 from that iterator, or then if that iterator is if we can't subtract 1 from that iterator to get the next lower value, then I go too bad. I say, okay, this is impossible. Otherwise, I erase this iterator, I erase the last position, and I insert this position instead. Sorry, I do that, and I do that right here. And then I add the value of this stone to our potential answer. And so then assuming that we get to this point without saying that our situation is bad, I set the result for this number of players to the maximum of its current value and the answer and our current value. And so then you'll see I set ResIF to the maximum of ResIF and ResIF plus 1 because anything we can do with I players we can do with I minus 1. And then I output the results. And that gets AC on the first subtask for 10 points. Now what about the second subtask for 10 points? For this one, I'm going to do a segment tree DP. And what I'm going to do is I'm first going to perform coordinate compression on the values t minus x, because t and x can be up to 10 to the 9, and I want to use them as indices on a segment tree. So I'm going to update them, update them so that now they're going to be less than n, and that way, and so here, so that we can use t minus I as indices on our segment tree. And that's valid because keep in mind, the only thing we care about at this point is the ordering of the t minus I. The values we don't care about at all. And so then again, I'm going to iterate in increasing order of x. Then query if the position p on our segment tree stores the maximum score such that our current t minus x is equal to p, our updates are of the form seg of p is equal to query 0p plus the value of our current stone. And so this becomes a fairly classical segment tree DP problem. We just iterate over the stones in increasing order of x, And then the idea is any stone that satisfies t minus x is less than or equal to the current t minus x and that we've already processed will satisfy both of these inequalities. It'll be increasing in t minus x, and x will be lower too because we're processing them in order of x. And so then we set this to the maximum value that's lower plus the value of the current stone. And from here we can print our maximum value overall, and that gets us our solution. Okay. So that's a segment tree DP. That's for another 10 points. Now for the final solution, or for the final subtask, 25 points. The solution here is to use min cost flow. And let me show you what my network looks like. My flow network that I built is essentially, so I've got a source, and then for all, and then what I'm going to do is I'm going to take advantage of the fact that min cost flow supports negative edge weights, and I'm going to say, okay, the cost of an edge, or I'm going to say, okay, so we're going to have 2 nodes for each stone, and each stone's and the edge between them is going to have cap 1 and cost negative c sub I, so that we actually gain c sub I points from taking this edge. And I'm going to have a structure like this for every pair of nodes, and I'm going to have edges with infinite cap and 0 cost. From the source to each of these nodes, and from each of these nodes to the sink. And then the one other thing is I'm going to have an edge from the second vertex of a given corresponding to a given stone to the first vertex corresponding to the next stone, if we can reach the second stone from the first stone. And so I'll show you what I do here, or how I do that. So here, these are edges. This is an edge from the source directly to the sink for any stones or for any players we just don't use at all. Here's an edge from the source to the first vertex for each node. I'm letting 2n be the source, 2n plus 1 be the sink, vertices 0 through n minus 1 be the first nodes for each stone, and n through 2n minus 1 be the second vertex. So this is the edge from the first vertex for a stone to the second. So this is where I get this edge right here from. This is an edge from each vertex to the sink. And then I have these n squared edges look like this, where they go from the second vertex to the first, or from one vertex to the next, if the first one has a lower x and a lower t minus x. And the complexity in theory is probably not good enough to pass, but you should know that min cost flow is usually performs much faster than its asymptotic complexity suggests, and so this ends up passing relatively cleanly. All right, awesome. So I think that's all I had. So I think I don't see any questions in the chat. So yeah, I think that's all. I guess a couple of things I'm going to plug. Obviously, subscribe if you're interested in seeing more of these streams and videos. I upload screencasts pretty regularly. I will upload my screencast from today's round, and so that will be up sometime soon. Also, if you're interested, I have a poll in my community page here if you want to vote for what sort of content you'd like to see next. But yeah, I think that's all. So thank you all very much for watching, and I will see you next time.